sorry. All right, so let's get started. So I'll hand back the exams. So the exams, we'll just talk about them briefly. So obviously it's a small class, so that doesn't help the distribution. But there are a few low scores, so I'm probably going to offer test corrections. And I'm thinking 75% back. So whatever you got off, right, then you can earn back 75% of that credit. And then, you know, if you did fine, you don't have to worry about that. Obviously, you can do corrections, but this is more for if you have kind of a lower score. And so the intention in this class, right, it's 100 levels, science class, so I'm not like looking to fail people, especially if you turn in the work and do all those things. So that's the main thing is, right, turn in all the other assignments and we'll kind of buffer out low test scores. And so I'll kind of think about too how to maybe change it up for the final as well. All right, so I'll give those back kind of during the class period. And so now we're continuing on, unless there are questions. So we'll be doing stoichiometry this week. So good lab for it. So we have our moles and chemical formulas lab, which actually lines up well with the chapter. I should mention there is an open flame though. So make sure to wear your cotton clothing, hair tied back. So another open flame lab. And of course, right, don't forget your pants, your closed-toed shoes, all those good things. Other questions? All right, so we'll keep going with our chapter then. And so now we're just kind of orienting ourselves. So kind of mentioning, okay, we briefly talked about chemical or physical changes where we alter our state. So state, that would be like state of matter. So solid, liquid, gas, right? Thinking of boiling water, taking an ice cube. To steam. You can also add to that, right, dissolving. So dissolving is a physical change, right? If you're making some nice Kool-Aid mix, we're just dissolving it in there. You could re-separate out the sugar and whatever else is in your Kool-Aid mix. And so, again, physical changes. Our atoms, our molecules, right, do not change their identity. So same formula, they're just, again, either dissolved or in a different state of matter. And so now we're going to be focusing more on chemical changes and not only kind of what is a chemical change, but of course how to write it out properly, which you got a taste of last week in lab, right? So that was a good lab for this where you're looking at chemical changes and then identifying, right, your reactants and your products. And so, of course, we can list examples of chemical changes. So we have iron atoms, and, right, you have probably seen a nail rust or maybe a bike rust or something undergo oxidation. Oxygen is in the atmosphere, and then those rearrange. And so it's nice to look at this little picture so we can appreciate how it is changing structure. And of course, right, that causes your nail to become compromised structurally and degrade, or whatever else is made of iron and rusting. And this is where naming compounds, so here's the other thing, right? Like, I'm not going to test exclusively on what we did in the first 4 chapters, right? But you're still going to have to know what to do with these names potentially. So iron 3 oxide, we have to be able to write the formula for it so we can put it into our chemical equation. So again, I won't be testing you necessarily on this, but writing formulas is still going to be important. So chemistry is cumulative by nature. And so just like you did for your lab, you're going to be writing your reactions. And this is also like super important. I can't understate this importance as a chemist, right? Because especially if you go on to grad school, do some reaction, this will be, you know, what starts every new page. It's like, what reaction are we going to be doing today? And so that's why it's always good to be able to write this. Again, if you're a chemist, you're going to be calculating amounts of materials every day, all day, every day, multiple times a day. So there's a lot of information kind of packed in this little statement. And so we can see we have reactants on the left side, products on the right. So there's some sort of arrow, right, indicating, and usually it goes in this direction in one way. So we're just talking about reactions that go to completion in this class. So you can, of course, take the 200 level of chemistry, and then that goes into more equilibrium reactions. But again, we're just kind of looking at straightforward reactions that go to completion. And again, there's a lot of information in here. So we have the identity of all our substances and also the physical state, which is important, again, for, right, a working chemist. How am I going to add this to the reaction? And so in this reaction, we can see we're adding kind of 2 gases. So there's the G. So we have G for gas, S for solid, L for liquid, and we also have AQ when it's dissolved in aqueous solution, just like we add many of our reagents in that form in lab, right? They're aqueous solutions of our metal salts. And then products on the right side, again, giving our states of matter. And then they should be balanced. Let's make sure. So this one is actually not balanced, so that's something that we'll look at. Let's keep going. So blah, blah, blah tells us how to write our equations, right? Again, we have to write our correct formulas, state our state of matter, solid, liquid, gas. And then the next important part that we'll be working on is our relative numbers of reactant and product molecules that are required. And then we'll see how this is related, because I mentioned, right, as a working chemist, you're going to be figuring out, well, how much reactants am I going to be throwing in my flask every day? And so now we can see that it follows the law of conservation of mass here. And so, of course, right, matter cannot be created or destroyed, so we have to account for the rearrangement of that. And so we can balance out equations by balancing out our atoms. And so that's just called stoichiometry. And so now the equation that we were looking at has been rewritten. So we can go back to this form. And so kind of what they've done is we just compare the number of atoms on both sides. And so, right, we have 1 carbon atom to begin with on our reactant side. And then I like to make a little chart. Okay, 1 carbon on our product. And then, okay, 4 hydrogens. Now we can see something is off, right? So 2 hydrogens. And so notice we're going to use coefficients to balance, right? So these are our product, or these are our chemicals. So now we have to figure out in what ratio. And so now we can use whole numbers to balance. And this is just kind of, it ends up being like a guess and check game. So if we have 4 here and 2, well, I'm going to just start with a 2, see how that goes. Okay, so now I have 4 hydrogens, now 2, so 2 plus 2, so 4 oxygens on my product side. And now I only have 2 oxygens on my reactants, so I'm going to put a 2 coefficient there. So now we're saying, right, we have 1 equivalence of methane reacts with 2 molecules of O2 to give me 1 CO2 and 2 molecules of water. So now if we go back down, so they got the same answer here, and so now they're just kind of visually showing it as well. So this could be just a nice tool to see how they're, again, just rearranged, right? We didn't destroy any oxygen atoms, they just attach themselves to carbon or hydrogen. So again, we just made sure we had the same number on both sides. And so now we want to understand, so what are we saying when we write this statement? And of course, right, they've shown us atoms. And so yes, we could be talking about individual molecules or atoms. And so now we're looking at this combustion reaction. So let's write that down. So combustion. So again, combustion reactions, at least our classic organic ones, have some sort of C, X, H, Y, and then O potentially, or maybe no oxygens. And then they're combusted. Obviously, combustion means that you're reacting with oxygen. And then the products of combustion are always CO2 and water. All right, so now this is the combustion of octane here. And well, we could be talking about individual molecules. So 2 molecules of octane react with 25 molecules of oxygen to make 16 molecules of CO2 and 18 molecules of water. But what's also nice is it also translates to the molar amount, and this is, again, usually the unit that chemists work in is moles. And so now we're saying 2 moles of octane reacts with 25 moles of oxygen to form 16 moles of CO2 and 18 moles of water. And you can also relate that to the atoms versus moles, right, when we're calculating molecular weight. Either we're talking about individual molecules when we look at our molecular weight on the periodic table, or we're looking at our molar weight. And so the other powerful thing is, of course, we can scale this by any ratio. And so this is just like a recipe, right? So if you need to scale up your cookies, right, by 2, you got to double your batch of cookies. Same thing with your stoichiometry, right? So now we could do it 4 moles of octane to 50 moles of oxygen gives us 32 moles of CO2 and 36 moles of water. Right, so again, scale it by any factor, so times 2 or times 100, it does not matter, right? It's just all about whatever scale you're performing it on. I'll just write it out to be explicit. And so you can tell, right, it doesn't matter. We're just scaling by this factor. Oops. And we could also scale it down by a tenth, right, up and down, it doesn't matter. All right, so now we're going to look at stoichiometry from the lens of making pizzas and s'mores. So food, again, right, we want to be thinking about making food. Most people like pizza and s'mores. And then, right, I just don't want you to forget everything that we covered once we move to chemicals, right? So don't let the chemicals scare you. And so now let's look at our balance reaction, right? So again, this is just like a recipe, right? You have your cookie recipe. It's got some ratio of flour to butter to sugar. And so we have here our recipes. So 1 crust plus 5 ounces of tomato sauce and 2 cups of cheese equals out to 1 pizza. And so we can express this, of course, in terms of these ratios. And then you also want to think about how these ratios will end up being your conversion factors, right? So essentially all you're doing for stoichiometry is comparing, whatever set of relationships, whether that be your 1 pizza to 2 cups of cheese, right? And again, just think about how you can set this up with our dimensional analysis. So, right, again, dimensional analysis is still here. It will come back. So there were some issues with some people on the exam with some unit converting. But then, right, unit converting is not going away. You're still going to have to do ratios. So same thing, right? We can set up a ratio where, okay, we have 2 cups of cheese. And for every 2 cups of cheese, I need 5 ounces of sauce. So again, right, you're just using your balanced equation to kind of get your ratio and conversion factors. And so now we can do basically our conversion factor. So now this example is set up. So now we're saying, okay, here's my recipe, here's my balanced equation. So now how much pizza then can we make from 10 cups of cheese? And so now we can set up our ratio. So they set it up for us, right? But go through it on your own. So they set up our conversion factor essentially. So we're comparing pizza to cheese. So then we go back to our equation, right? So we can write our ratio. Well, for 1 pizza, we need 2 cups of cheese. Then they set up their dimensional analysis. And again, let's just walk through this. And so we begin with 10 cups of cheese. Set up our dimensional analysis. So we want to figure out how many pizzas we can make. So pizzas goes on top. Cups of cheese goes on bottom. And that cancels. So cups of cheese cancels. We have 10 divided by 2. And so now we get 5 pizzas just like they got there. All right, so now let's repeat that. But now we want to do it with s'mores. And so let's just start off with our balanced equation. And so I was saying we probably need 2 graham crackers. And then we'll use 1 jumbo marshmallow here. And 3 pieces of chocolate. So that gives us 1 s'more. And so now let's just start off with something relatively simple. So let's just say we want to make, let's make 25 s'mores. So how much of each ingredient do I need? So take a minute or so to look at that. So now, how many do we need of all these ingredients? So how many graham crackers? So 50 graham crackers. And so this starts off simple enough, but again, just kind of go through it. So you have 1 s'more here, so times 25. And so now 2 times 25, so okay, 50 graham crackers. Excellent. So then how many marshmallows? 25. So 25 marshmallows. And how many chocolates? So 75 chocolates. Good. All right. So now let's look at another type of problem. So kind of a limiting reagent problem. And so now let's ask, and so same equation. And so now if I have 77 graham crackers and excess marshmallows and chocolate, how many s'mores can I make? So how would you solve that one? So how many s'mores did we get for this one? So 38.5, that sounds good. And again, right, think about the process. So you had 77 graham crackers. Again, you're comparing your mole ratio, whether you realize it or not, right? So for every 1 s'more, you have 2 graham crackers. So then you can set up, again, your dimensional analysis formulae, and then, yes, 38.5 s'mores. All right, that's good. So let's try, I'll try another kind of limiting reagent problem, they're called. And so now let's compare. So if I have 321 chocolate pieces and 178 graham crackers, and let's just say excess marshmallows, how many s'mores can I make? So how's this one going? So do we have an answer, or we could talk about the process too, because you kind of have to do this twice essentially. So let's find out what you got. So we did 321 chocolate pieces. If I could spell chocolate. And then again, right, we just look at our balanced equation, get our conversion factors. So 1 s'more requires 3 chocolates. So how many s'mores could we make from this amount of chocolates? So 107 s'mores. And then of course we're not done though. So now let's repeat that. Now for our graham crackers. So 178 graham crackers. Again, comparing what's essentially our mole ratio. So 1 s'more requires 2 graham crackers. And so how many s'mores was this? So 89. And so now which one is our least amount? So 89. And so I'll say our least, right? So then we can say that our graham crackers is our limiting reagent. And limiting reagent just means that it runs out first. And again, right, these are fancy terms for chemistry, but you probably do this at home potentially, right? You're trying to make a cookie recipe. Well, you got to kind of gauge your ingredients. How much flour, how much sugar, how much butter do I have? Do I have enough ingredients to make this cookie? Do I have to do some substitutions? You know, what has to happen? So you're doing that at home, and now we just kind of want to apply that to chemistry. All right, so this is good so far. And so kind of, let's again just recap and think about what we've done here. And so all this was just kind of using our mole ratio comparison. And so that's easy enough, but we want to be able to take this a step further. And so usually in chemistry, you're not just given a nice molar amount, you're given some sort of grams, right? Or you go into lab, you recover some amount of product. Well, you got to figure out how many moles of product that translates to. So let's continue with our same s'mores equation. We're just going to add some numbers to it. So we still have our 2 graham crackers. I'm just rewriting everything. Plus our marshmallow. Plus my chocolate pieces. And still makes 1 s'more. And so now we'll add some molecular weights to them. So again, right, you all know how to calculate a molecular weight. You go to the periodic table and add everything all up. But I'll of course give you our molecular weights right now, because obviously that doesn't work. So our molecular weight for our graham cracker is 55 grams per mole. Our marshmallow is going to be 70 grams per mole. And 1 chocolate is 15 grams per mole. And so now just start off with what then is the mass of 1 s'more. So what do we get for this one? So we just have to add everything up. What do we get for our mass then of once more? So 225, that sounds good. Is that what other people got? So 225, I forgot to fire up my calculator. That sounds correct. So again, just multiply everything by the correct amount. And so in this case, it's easy to mass balance since we only have one product, but generally I don't recommend mass balancing. So 225, excellent. So 225, so that's our grams per mole, so our molecular weight. And so now let's try the types of problems that we'll see, again, with chemicals. And so you can do it with marshmallows, you can do it with chemicals. And so now let's say, so if I have 777 grams of graham crackers, how many s'mores? So what steps do you have to do now for this one? And so what do we have to do for this one? So kind of walk me through, what did you do first here? We have 777 grams of graham cracker. So what do you do with this? You could also just tell me what you did mathematically, if that makes more sense. So what do you have to do? So divide by 55. So exactly, right? So think about what this is related to. So again, right, it's our molecular weight essentially, but we're trying to figure out, well, how many graham crackers do I have, right? How many moles do I have? And so that's what you're trying to do. is go from grams to moles here, so we can get back to our balanced equation. And so now let's do that. So we have our relationship. So again, 1 mole of graham cracker is 55 grams per mole. And right, notice that, so you have your grams per mole. So 55, if it's going on bottom, 1 mole's on top. Okay, so that gives us how many graham crackers? And then from there, so we just want to keep writing out our dimensional analysis. Right now, we can solve for how many, and then plug it back in to our formula here, to our balanced equation. And so we can say, well, 1 s'more needs 2 graham crackers. So then how many s'mores do we get? And we can multiply across. So 777 grams divided by 55. So we got about 14 graham crackers. But then from our 1-to-2 ratio, so we get about 7 s'mores there for that one. Does that make sense to everybody? Yeah.
If I divided the 777 by 110, will that still be correct? Since 1 s'more is made up of 2
Yeah, 2 graham crackers. You probably don't want to do that because it'll mess you up later, potentially. So like, yeah, you're like correct in that. But once we do chemistry and like continue on, it'll be confusing. So yeah, don't do that. Just do the mass of one of these. So right, if we're doing molecules, you just want to calculate the molecular weight of, magnesium phosphate and get 1 molecule.
step by step?
Yeah, because like I said, otherwise you might confound it. Let's do 1 more before break. And so again, let's do a limiting reagent type problem. And so we just want to continue practicing it with the s'mores, but then you're going to kind of see the process and see how it can also be a little tedious sometimes. So if I have 420 grams of marshmallows and 334 grams of chocolate, how many s'mores can I make? And of course, assume excess of our graham crackers in this case. So again, think about the steps that you're doing, kind of think about how that will translate to chemicals. So let's start going through this one. So just kind of going through the math. So again, right, thinking about what we're doing, we have some sort of gram amount. So I'll start with the marshmallows. And we need to go from grams to moles. So now I'm dividing by the molecular weight, so 70 grams in 1 mole of marshmallow. And then again, back to our balanced equation here. So for every 1 s'more, we need 1 marshmallow. So how many s'mores did y'all get from this 420 marshmallows? So 6. It sounds like people agree. So 6 s'mores. And then we have to repeat that, right? So that's, again, I don't know if it's the issue, but, you know, it's kind of the tedium, we'll say, of these problems. So yes, you have to kind of do it twice. And so 334 grams now of chocolate to compare. Again, same process, dividing by the molecular weight to get to moles of chocolate. And then now moles, we can use our balanced equation. So 1 s'more requires 3 chocolates. And so how many s'mores did y'all get from this? 7. So 7. And so of course, if 6 is our least amount, then this is our limiting reagent. So our marshmallows are our limiting reagent, and yes, we can only make 6 before we run out of marshmallows. All right, so that's probably a good stopping point for a break. So we'll take a 10-minute break. I'll probably go print out some mole highways, and then we'll do one more marshmallow one, and then we'll move on to moles. Go ahead, take your break. Hand back. Yours is at the testing center. So, yeah, anytime. All right, before we look at the mole highway, let's just tackle our last kind of type of question that we'll have. And so there's a percent yield question is what it's called. And so there's, different ways that this could be asked. You might have to find the percent yield, or maybe you know it. And so let's just go through kind of one example. And so we expected to make 60 s'mores. And again, right, this number could either be given or maybe you have to calculate it, right? It's going to ask, okay, based off of this, how many s'mores you have to make. Okay, so then if we expected to make 60, however, we got too hungry and only made 56 s'mores. So what is the percent yield? And I'll give you guys a formula. And so anytime you're asked for this percent yield, what it's going for is there's an equation where it's actual over our theoretical, and then of course times 100 to get it as a percent. And so let's again think about what this is referring to. So right, our theoretical yield, this is what we calculate essentially. And again, you're usually given some sort of problem, blah, 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 just like we saw up here, that, okay, we had 420 grams of marshmallows, 334 grams of chocolate, right? You calculate your theoretical yield. So, right, we figured out theoretically we should have 6 s'mores, but then actual, right, you have to be given. So it's either what happens in lab, so in lab, right, you would record that, what you actually have in hand. Otherwise, it's given to you, like in this problem. And so we can just work through this one together. So in this case, right, this is our actual. So after, spilling it on the balance or whatever happens in lab, right, we accidentally threw half of it down the drain, and now I only have this much product, right? That's what we actually have. And then we want to compare it to the 100% yield. So again, that's all what the theoretical means, that, if we could get 100% recovery, everything was perfect, how did it go? And so in this case, we just take 56 over 60, since again, we were given our theoretical yield in this problem. And then convert it to a percent, so about a 93% yield there. And so something else to kind of think about is, well, why is this relevant? Of course, again, in Gen Chem, we only do these like one-step reactions, but let's say you were trying to plan a synthesis. And so even a relatively small synthesis, so let's just say you had a 7-step synthesis and you had a 90% yield at each step. And 90% sounds pretty good. That's what organic chemists tend to aim for, is over 90. And we can see, so what's our yield then by the 7th step? So you could see how to calculate that. So that would be 0.9, right, times 0.9 for every step, which is, of course, just 0.9 to the power of 7 then for a 7-step synthesis. So now let me use my calculator. And so by the time you do that 7-step synthesis, you're already at a 47.8% yield. So not that great. And like I mentioned, this is a pretty small synthesis, so typically an organic synthesis could be like 20 to 30 steps. So you can quickly see how that diminishes, right? 20 steps already turns into a 12% yield. And again, just using 90 at 30 turns into a 4% yield. So, I mean, obviously we don't have to think about that in this class, but that's obviously why chemists want to try to get 100% yield as possible and why they might look for different reactions. And this is also where you start to hear horror stories of poor organic students who are maybe doing a 20-30 step synthesis and then they accidentally mess up. So I've heard of drain extraction horror stories. So whoops, product went down the drain, and then you get the U-pipe out and have to do an extraction. Because again, if you're talking about 20-30 steps and 12 or 4% yields, right, you're pretty desperate at that point. I've also heard of rotovap extractions. So we don't have a rotovap in here. Let me get a picture of a rotovap so you know what the heck I'm talking about. So this is a rotovap. All it does is take solvent off. So you have like your product here with solvent, and then this is just hooked up to vacuum and it dries your product. However, sometimes people mess up and this bulb falls into, this is a water bath here. So it falls into the water bath, goodbye product, so then you have to do an extraction from this water bath. And I've heard of, again, poor students doing that in desperate times. So that's why they get so desperate when you're trying to recover a small amount after a long synthesis. Anyways, so now let's look at our mole highway handout. So kind of, again, we're thinking of how we're going to translate our friendly food to our moles. And so, yeah, I've just printed it out, so it's there. And so we can kind of look at it. I'll give people a second to grab a copy. And so kind of the idea with our mole highway is we have moles in the center, and I always like to say, right, this is kind of our safe space here, since we need to be in moles to be able to, again, compare the mole-mole ratios. If you're in moles, right, that's usually a good thing. And then this is just to kind of help you remember how to get back to moles. And so we'll do some more problems and see some of these other scenarios probably Wednesday if we don't get to them. But of course you can use your dimensional analysis, but again, this is kind of a good sanity check. And so we'll be doing a lot of right mass to moles or vice versa. So if we're given mass, it reminds us, okay, divide by the molecular weight to get moles. So that's kind of nice, right, to just double check your dimensional analysis. If you're trying to go from moles to grams, just a little reminder, right, multiply by the molecular weight. And then, right, moles to moles, so trying to do our mole-mole ratio. It reminds us to use our stoichiometry from our chemical equation, right? So again, just comparing the balanced equation. And then, like I said, we'll look at this conversion factor a little later. I have to look at our homework examples. But we can at least write out what our conversion factor is. So this is Avogadro's number, which again just defines how many particles are in a mole, so 6.022 times 10 to the 23rd, and that's going to be atoms or molecules are in 1 mole. And so again, this funny number, this Avogadro's number, goes back to the periodic table, and it has to be that number such that, right, like we said, this has to equal to 14 atomic mass units, and it has to also equal to 14 grams per mole. And so if you were to multiply 14 atomic mass units by 6.022 times 10 to the 23rd and convert that to grams, you would get that molecular weight back up. And then this, we haven't quite touched on this, we won't do too much density in here, but let's just say you were given a substance, you know, that's obviously not water, so water has a density of 1 gram per milliliter. Otherwise, right, you have to take into account a substance density if you're using, again, this would be for a pure liquid. So this does not have molarity on there, so that's something that we'll tackle in another chapter. All right, so that's a nice guideline. And again, just kind of more helpful hints here, reminds you of Avogadro's number. All right, so now we want to take all our knowledge and apply it to chemicals. And so again, right, we're back to our combustion equation. So less tasty than our pizza recipe, but the whole point is, of course, we're looking at our stoichiometric ratios. And so it doesn't matter which ones we're comparing. So they picked our octane versus CO2, but basically, right, we can establish our conversion factor, so our relationship between any two of our molecules here. And so it's just emphasizing that, right, we can make conversion factors for anything, essentially. And so again, I'll just kind of call them conversion factors. And we can, again, write them in our fractions, so that helps you to kind of see this, right? So it doesn't matter how you express them, it's just a relationship depending on which way we're going, right? We may have to use this in different forms. Yeah?
How come in this case the octane is in liquid state?
I mean, that's just,
Oh, it doesn't matter? Okay.
yeah, I mean, so octane is going to be a liquid.
Oh, I thought it was always an aqueous solution. Oh,
Yeah, it just depends what it is. So that's why, yeah, so like octane, right, that's kind of like an organic.
yeah.
So that's like the gasoline that you put in to your car. So yeah, so that would be in a liquid form, octane, doing the combustion.
Even with the water here, is it in a state of being a water vapor?
Yeah, so according to this one, and you know, you could get, because this is probably going to be a gas, right? Because again, these combustion reactions are happening at high temperature anyways.
So
that,
there's heat that is involved.
yeah, for a combustion, but I wouldn't necessarily get like too hung up on all these states.
Oh, okay.
So yeah, like obviously you'll try your best, and most of our reactions, like, you know, we'll be doing precipitation reactions, obviously those will be aqueous, but others, you know, like if you didn't know this, I don't think that's that critical, but it's good knowledge, right, for the chemist. So that's the thing, is like, okay, as a chemist, I know that this can be added in the liquid state. So, right, so again, this is our combustion reaction.
I saw a small triangle under the arrow.
On,
It says when the products are being heated, you're supposed to put the enthalpy or the trienthalpy.
yeah.
Is it really necessary for me to always put it? Because here I don't see it.
I mean, it's honestly inconsistent.
Mm-hmm.
Like, that's what you notice. You should put, it's like, yeah, there's a little heat sign. But usually that means that you're like actively heating too. So like I wouldn't put it here for a combustion reaction. So even though a combustion reaction is burning and is exothermic, you just like usually don't put like the heating conditions for that. But then like there could be other reactions where it's like heat, you know, at 130 degrees Celsius. So it might have something like that where it's actually giving you temperature conditions, right? Versus just like a combustion is just going to go and you're not gonna, you know, baby it at a certain temperature. All right, so now, so you might want to write down this equation to help you. So 2 moles of octane to 25 O2 to 16 CO2 and 18 water. And so now let's try our practice. I'll let people write that down. And so before I scroll down, just try to set up this problem, right? Because we just did it with our, again, our s'mores. So how many moles of CO2 form if 22 moles of octane are combusted? So let's see how y'all are doing. And so they outline the solution for us. So again, right, you had your balanced equation. And then you can look at what it's asking for, right? So we're comparing moles of CO2 to moles of octane. So I would look at those. Okay, there's octane, there's CO2. And then they set up their ratio. And of course, right, they write it in this form. I always like looking at it as a fraction, since we're going to have to use it in our fraction form, either, again, in this manner or with 16 CO2 on top. Okay, so now we have, again, just our conversion factor relationship. And so now we can set up our stoichiometry. And again, they outlined it pretty nicely, but I'll just rewrite it. So we began with 22 moles of octane, right? And then octane goes on bottom now to cancel out. So I'm picking this conversion factor to plug in. So 16 CO2 on bottom, 2 equivalents on octane on the bottom. So octane cancels. And then we're left with our math here. So 176 moles of CO2. Did we all get that? So again, ask questions on this, but it is just a lot of practice. And so again, this is just kind of outlining our strategy and typically how these problems go, which is again what we were trying to practice with our marshmallow stoichiometry, is that usually you're given some mass of something. So again, right, we did that with our marshmallows and graham crackers. We started with mass, and then we convert to moles. And so again, right, that's where this mole highway is useful. Okay, we always have our moles. We always want to be able to get to that. And then we have our ratio, or again, right, our conversion factor between whatever we're looking at, A and B. And then we convert to moles of B. And then if we need to go back to mass, of course, again, we can, right, multiply by our molecular weight to get back to grams there. Since usually the problem, right, will want us to calculate a gram amount. And then this is just, again, the math setup of that, just what we've been practicing. All right, so let's tackle this one. So again, don't let big numbers intimidate you. So now we have determined the mass of CO2 produced when 3.6 times 10 to the 15th grams of octane are burned in excess oxygen. So see if we can start that. You might have to calculate some other information. So how's our problem coming along? And so this outlines our strategy at least, but then y'all can walk me through the math then and help me, because we probably are missing some things, right? So we're starting off with 3.6 times 10 to the 15 grams of octane. And so they kind of give us this strategy. So of course, right, we always need a balanced equation, but we already had that. And we have our mole ratio, okay? So where do I need to go from here? And maybe what other extra info did you have to calculate?
The molar mass of octane.
So excellent. So molecular weight of octane. So what do we get for that?
114 grams per mole.
So 114 grams per mole. And again, right, your answer could vary. So I probably would have given it at least something after the decimal point. I have like 0.232 in my notes, but you could have gone to like 0.2, 0.23, or if you left it at 114, that's also okay, right? We only have two sig figs here. So, okay, there's already a small discrepancy, so just keep that in mind. So again, your answer could vary slightly. So good, so we have 1 mole of octane was about 114 grams per mole. Excellent, so that gives us, right, moles of octane, so just kind of keep track mentally of what we're doing. Then we have, right, our mole-mole ratio. They kind of fed it to us funny. Again, I like putting it in our conversion factor. Thank you. So exactly right. So set up in this form such that the octane cancels out. So make sure you see that. And then last bit, so it asked us the mass of CO2. And so of course the last bit, right, this gives us moles of CO2. So now we need to multiply by our molecular weight. So do we have a molecular weight of CO2? So about 44 grams per mole. And that's where I rounded it in my notes. Again, right, if you had different rounding, that's okay. All right. So did we all get this for the setup at least? So kind of make sure you can do this setup, right? This is your dimensional analysis. Back to haunt you. And so now we can just multiply across. So I'm just going to plug it in. So 3.6 times 10 to the 15 divided by my molecular weight times my 16 over 2. So I'm just going to multiply by 8. And then times 44. And so let's see. So did we get this for our mass? So 1.1 times 10 to the 16th grams. So at least one yes. Is that what other people got? So 1.1 times 10 to the 16 grams of CO2. Questions? Ask questions now. So yeah, the 44 we had to calculate ourselves. So right, we had to add up our molecular weights for CO2. So let me just pull up, right, so from our periodic table, roughly 16, so 16 times 2 plus 12, so that's 44. And again, right, could have gotten slightly different answer with rounding. I think 44 works pretty well in the rounding there. Other questions?
Is there a difference if I write 44 grams per mole and 44 grams?
So the difference, right, is you want to define it as grams per mole, because then you're saying, right, that 1 mole is 44 grams. Otherwise, you're just saying that you have 44 grams of something. And then question?
Under 44 grams, what do you write? Is that molecular weight? Right there, yeah. What is that?
Oh, mole there, right? Because you just want to say that 1 mole of CO2 is 44 grams, so you have your ratio. Other questions on this setup? So now we can try another one. And so I'll at least give you our hint, right? So we're starting with our balanced equation at least, but that's something that you should always check. So I think that's part of your homework too this week, is just like practicing balancing equations. And so again, just check that you have a balanced equation. And then think about what else you have to calculate, right? Just like we had to calculate our octane molecular weight and our CO2 molecular weight. You're going to notice that's a theme of these problems. So you might need the molecular weight of something. So I'll let you start that, and we'll go over that. So let's just kind of see where everybody's at with this problem. So what extra information did you have to calculate before you started diving into everything? So we're asked to find, right, our mass of HCl and neutralized by dose of milk of magnesia containing 3.26 grams of magnesium hydroxide. So what information do we need?
The molar mass of magnesium hydroxide and the molar mass of hydrochloric acid.
Excellent. So what do we get for, let's hear magnesium hydroxide first.
58 grams.
58, is that what everybody got?
What is the ideal decimal place that we should round off?
I would usually go to like 2 after for molecular weight. So, yeah, do we have 58 something? Sorry, I was looking. Anybody go out?
Can be 58.29.
So 58.29, or again, right, you might have another answer. So grams per mole. And then what other molecular weight do we need? You said HCl, correct?
Yes.
And so what do we get for that one?
36.45.
So about 36.45 grams per mole. All right, so now we can set up our stoichiometry. So again, right, if you need to, I would kind of look at this strategy. So this is, right, your strategy hint page. So basically, okay, we need to go from our mass of A, which is our magnesium hydroxide, get to moles. So we'll divide, right, by the molar mass of A. So it's kind of outlining it. Then do our mole-mole ratio and go from there. So let's do that. So then we have 3.26 grams of magnesium hydroxide. So divide by the molecular weight. And then setting up, right, mole-mole ratio. So we can tell we have moles of magnesium hydroxide. And so now I want to compare our balanced equation. And so this is for every 1 equivalent of magnesium hydroxide, we need 2 equivalents of HCl. And so I want magnesium hydroxide to cancel. So that will go on bottom, 2 moles of HCl on top. So any questions so far? And so right now we're at moles of HCl. It wants mass though. So right, last step is now we'll take our moles of HCl. So 1 mole of HCl is 36.45 grams. And so now let's plug this all in. And so I get about 4.07 grams, or 4.08, so we want to round to 3 sig figs. So 4.08 grams of HCl. Questions on this one? questions? Still writing, maybe? Let's see if we can, I don't know how far we'll get on this problem. And so again, right, we'd mentioned, okay, we sometimes do these limiting reagent and theoretical yield problems. So again, our limiting reagent told us which one's going to be consumed first. Obviously, the excess one is the one in a larger quantity. And again, our theoretical yield is how much we're calculating based off of that limiting reactant. And so let's see if we can at least start this one. And so ammonia can be synthesized by this reaction. So 2 equivalents of NO plus 5 equivalents of H2 give us 2 equivalents of ammonia. And so now it looks like this is a limiting reagent problem. So we have 86.3 grams of NO, 25.6 grams of H2. So what is our theoretical yield of ammonia in grams? So let's just kind of talk key points, and then we'll probably have to finish this up on Wednesday, going over the answer. But kind of, so what other bits of information do we need to work through this? So what molecular weights? So we have 86.3 grams of NO, 25.6 grams of H2. We want theoretical yield of ammonia. So what do we need before we even get into it? What did you say? So not hydrogen percent yield, but we need molecular weight, right? So we need hydrogen molecular weight, we need NO molecular weight, and eventually we'll need ammonia. So what's the molecular weight of H2? So 2 or like 2.02 or something. So again, just don't forget that it's diatomic. And then what's the molecular weight of NO?
29.99 grams.
So 29.99 grams per mole. So that sounds good. And then what's ammonia?
70 grams.
So 17 grams per mole. All right, so we'll probably have to stop there. Like I said, we'll finish this up on Wednesday and do more practice, but see if you can finish this up at home, right, if you didn't already. And so again, right, I'll point back to this page. Here's your strategy. So mass to moles to ratio, back to moles and mass. So write this out, write these little helpful hints, so that's useful, right? That'll get you going. And see if you can finish it up. And then, like I said, we'll go over this on Wednesday, and then we'll keep doing more stoichiometry practice so you can really get this hopefully under your belt. We'll look at some homework practice problems and maybe your lab as well. All right, so don't forget open flame lab on Wednesday. So hair ties and cotton clothing.
I wanted to know this question. So here it says that it has 19 electrons. So then the 19 electron